Alright, so we're going to be moving on to the 24th problem in the grind 75. This one is called, let's see, maximum depth of binary tree. Okay, we're given 15 minutes. We'll start the countdown now. Okay, let's see. It's loading. Wi-Fi should be okay. Okay. So given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So root to farthest leaf. Okay, so this seems like pretty much the same problem we did before where we were trying to find the maximum diameter. It's just that we don't have to find the maximum diameter. Instead, we have to get the maximum height. So I'll just make a global variable called max height. We're going to initialize that to 0. And just to keep things consistent from last problem, I'm going to make another function. This one's going to be called depth first search. And it's also going to take in that tree node root. We might not even need to make that second function. I'm just kind of setting it up in the way that we approached the problem last time. But let's remember what we actually did first. So we had some base case, then recurse on left and right, and then we would start to get the height. Yeah. We would get the height, and that would actually be returned. So I don't even think we need that global variable. Yeah, because we can just call this on left and right and then get the maximum of that. I feel like we've already done this problem. Return its maximum depth. Well, I don't know. Let's just, I guess we'll just go through it then. So, can we have, yeah, we can have 0 nodes. So I'll just have that base case. Root is equal to null. Then we're going to return root. I guess it has to be an integer. Return its maximum depth. I guess it would just be 0. Then we're going to call, let's say, integer left height equal to depth first search on root dot left. Similarly, did not want to do that. Similarly, we'll call this on roots dot right and call this right height. And then we are going to return the maximum between the two. It's going to be left height and right height. Okay, and now for the actual logic of the problem. Again, if our root is equal to null, this happens after we've checked if the initial root is equal to null, meaning the root must have at least one node, or the tree must have at least one node. So once we recurse down to the left or the right, we're going to check if that's null. If that's the case, then we're just going to return 0. Otherwise, we are going to return the maximum of yes. Is this right? Yeah. The maximum of the depth first traversal on the left of the root and the right of the root, and then we're going to add 1 when we hit the base case. So just to go over the example that is given to us, let's say we start off with 3. The root is not null, so we're going to travel down the left. Let's just look at that recursive call. If root equals null, return 0. Otherwise, return 1 plus DFS on root left and root right. Both left and right of these are equal to null, so they'll both return 0. Maximum will be 0, but will return plus 1. And so that gets put into left height. And then right height, we go down to 20. Go through DFS. Our root is not null. And so we're going to return 1 plus DFS on left and right. So let's go down left first. Left is still not null, so we won't return 0. And then we'll go 1 plus DFS on the left and right of 15. And both of those will return 0. So 1 will get pushed up back to here. And then 2 will get pushed back up to 20. And similarly, hold on. So 1 will not get pushed back up to here. Actually, 1 will get pushed up to here. Same, this will be a height of 1. And then going back up, that should be a height of 2. But let me just go through that one really quick again. So we go down right. Then we're going to return 1 plus whatever we get here. Then we go down left. We can return 1 plus whatever we get here. Going down these both yield 0, so then that 1 plus goes back up here, and that 1 plus goes back up here. Okay, yeah, that seems to work to me. And this should be, runtime-wise, this should be, or I mean time complexity-wise, it should be O of n because we're traveling down to each node just once. And as we're going back up the recursive stack, we are generating the height. But we are only actually physically traveling to the nodes once. An algorithm that I used in another problem had us get the height of left and right, or I had us do something similar to get the height of left and right, and then get the height of left and right's subtrees, and so on, which would turn out to be O of n squared time, because we would be looking at all the nodes initially, and then we'd be looking at one subtree's node in all the nodes in that subtree, and so on. And so that would end up costing us O of n squared time. But this should not. And unless I'm missing something, this should be the solution. So let's see if we always have some syntactical errors. Oh, well, we just got the wrong answer, I guess. So 3, 9. Okay, that's this tree right here. Output return is the maximum depth. That's 1, 2. Expected 3. Wait. Is the number of nodes along the longest path. Oh, number of nodes. Yeah. So it's not number of edges, I guess. I guess we could just add 1 right here. Does that hold up for any base cases? Say we just have a single node with null leaves. Recurse down here, both return 0. Yeah, okay, that should work, I think. Okay, and then let's submit. It's taking quite a while. I think that's just my Wi-Fi, but okay, cool. Yeah, so that was pretty straightforward. We'd seen a more difficult problem in the past, but the only thing that got us was a little technical issue where I was asking for the number of nodes and not really, not the depth, as in the number of edges. that concludes the attempt of this problem.